So we're going to continue our kinetic journey and look at another way to find rate law. If you remember yesterday, we looked at a way to, or rather the way was to look at the mechanism of the reaction and write the rate law from the mechanism. However, the mechanism was unable to give us a K value. All right, all it was the rate law, which is good and useful. But today, by using a method called initial rates and table inspection, we'll get to actually do a calculation to find K. So make sure that you have your slides out. Those of y'all at home, click slides on YouTube or get them out. If you are a part of my class, I'm going to go eat something. It looks like it's hot Cheetos. And what do you call these things?
Munchies.
Okay.
Eat it.
Or, so on chemistry,
How are you, Mr. Cummings?
can't handle it. Okay. Now, here's the thing about calculating K though. When we actually get to plugging values into a rate law, there's a bunch of funky units existing. Like there's a liters times moles over seconds, and then on the other side, you've got seconds on top. There's a lot of weird things that happen with the units. I find it easier, instead of doing the algebra after you get the number to find out the units of your answer, to just memorize the units. If you have the units on this slide memorized to the point where if it's a second order reaction, you know what to write after the K, I think it goes faster. So that's your call. We can sit down and go over the manipulation of algebra, of course, but I think that this will serve you well.
It's algebra we already know, right?
Yeah, but there's just letters all over the place. Like it looks like the alphabet's rebelling. Ha.
That's a good one.
Right out of boom, right top of my head. Anyway, thank you. Okay, so you have those there on your slides. You'll want to use them to your advantage. So, method of initial rates, our second way of finding rate law. The way that this works is instead of having a reaction showing us the mechanism, we have the reaction and we actually got some lab data. We're going to do the reaction in multiple trials while purposely only altering one reactant at a time. What that does for us is if we have our first reactant and we keep the molarities the same but alter the molarities of the second reactant, we can see how that second reactant is affecting the kinetics on its own. And then if you do more trials where you leave that second reactant constant and alter the molarity amounts of the first, you can see what happens to the rate there. And by comparing those values, you can come up with orders like you want, and as you'll see, a value for K. You can swap. So we can dive right into our first example. We're only doing 2 problems today. It's my belief that you'll think today's easier than yesterday, which is why it's going to go a little bit quicker. But let's take a look at the data that is happening here with nitrogen dioxide and fluorine. It looks like the experiment was ran 3 different times, and you can see that we have different molarities of each reactant that have been assigned. But you'll also see that the lab data produced the rate by which products were being made. All right, and that is the rate that we didn't have yesterday. That'll fit right into our rate law here in just a little bit. So here's the trick. We need to find the orders of those 2 reactants, all right? But we don't have a mechanism to do it this time. We're going to do it in a more mathematical way. As I said, the reason this works is by looking at trials where one of the reactants stays constant. So let's start off by looking at NO2. What I'm trying to find is that value right there. I want to know his order. In order to do that, I'm going to focus on the 2 experiments where the other reactant stayed constant. So I want you to look at the 3 trials. Do you see the 2 trials where F2 stayed about constant in molarity? Trials 1 and 2, all right? Those are the trials then that I want to look at the change of this guy to figure out his order. So we said we're going to use trials 1 and 2, all right? What I'm going to do is my first step is I'm going to divide, using just those 2 trials, the larger number by the smaller number. So in this case, it's going to be 0.0482. That's trial 1's information on NO2, divided by 0.0120. That's the trial 2 information on NO2. Are you with me? All right? And we're going to get a quotient there, and the person that's going to yell that quotient is cluster 1, seat 3. Now, while she's finding that, this intermediate steps during table inspection is going to give you pretty whole numbers. So if you get, for example, 6.999997, this part will give us nice, pretty whole numbers.
I got, wait, hold on. 6 pigs count?
I just want a whole number. 4. She got 4. All right? So far, all we've done is we divided NO2's data using the trials where the other reactant didn't change. Now, the other thing that we want to do is figure out, okay, well, to what power would that number need to be raised to equal the rate change for the same 2 trials? Now, if you look at the last column over there, you see the rate changes. Remember, we divided trial 1 by trial 2 just a moment ago. I want to do the exact same thing, but using the rates this time for those trials. So, in other words, I'm going to divide 1.90 E negative 3 by 4.69 E negative 4. You'll notice it's the exact same 2 trials being divided in the exact same 2 ways, but just the different column of information, the rates. And the person that's going to shout that out to us is cluster 1, C2. She got a calculator. Hey y'all, there's 1,000 calculators in the back of the 1,003. Yes, sir.
Why are we dividing?
Because that's the way for us to find the rate change.
Got 0.04. I don't know if that's...
You slid something in here. Anybody else get a different number? 4. Yeah, I get 4 again. All right. So here's the trick, guys. We're wanting to know, okay, well, my initial change in molarity raised to what power will equal the change in rate? So in other words, 4 to what power equals 4? 1. And that number right there is the x. So in other words, my order for NO2 in this case, well, doesn't get an exponent because we don't show ones. Yes? Yeah. When using a method of initial rates, it'll always give you an initial rate.
Would there be one where the mole or molarity, moles, no, molarity would be that one of them would be bigger than the initial rate would be smaller?
No,
Okay.
because by increasing the molarity of your reactants, you should increase the speed.
All right.
Okay, so, but now we need F2, all right? We want to know, well, then what is the order of this guy? Same thing. We want to run numbers using 2 trials where the other reactant did not change. Which 2 trials will we use this time?
1 and 3.
1 and 3. Trials 1 and 3 has NO2 remaining almost constant. So now we're going to do the same thing. We're going to divide the larger number by the smaller number. So I'm going to go 0.127 divided by 0.0318. Because we're using trial 1 and 3, because that's where the NO2 didn't change. And to keep our numbers above 1, we always divide the larger number by the smaller number.
So the negatives and stuff won't apply for this one.
No. So let's go to cluster 3, seat 4 for the answer. Hey, instead of y'all being surprised when that hits you, you could just all get the answer, and then voila, you're ready. She got 4. All right. And our question, remember, is 4 to what power would equal the rate difference between the trials? So let's run the rate. Now, you got to do it in the exact same way. We're using trials 1 and trial 3, but dividing the rate of 3 by 1. So we're going to go 7.57 e negative tree divided by 1.90 e negative 3. And the person that already found the answer is cluster 6, seat 1.
Is that me?
Totally.
Oh my god, 4.
He got, oh my God, 4.
Because there's only one I'm going to remember, and that's 4.
What's the missing exponent here? 1. All right. Therefore, the order of fluorine is also 1. And now we have our orders like we were able to find yesterday. So let's continue.
Wait, so why do we do the fluorine? Why do we do 1.97?
Because we can only use the 2 trials where the other reactant didn't change.
Oh, it's the other one.
Right. Because whenever one of the reactants isn't changing, that means all of the data is coming from the reactant that is changing. So we found the reactant orders. All right. Hey, look, the reaction order. What's the reaction order here?
2.
It's a second order, because how do you find reaction order?
1 plus 1 is...
You add them up. You 1 plus 1. You waited for that part in AP Chem where the answer was 1 plus 1. It's a second order because of the sum of the individual orders. Okay, what about the rate law? We can write a rate law. We know how to do that. The format for a rate law is rate equals K, and then each reactant to its order. NO2, F2. Of course, these have a power order of 1, but we don't show ones. And that's where we were forced to stop yesterday. However, we've got more information this time. If we want to calculate K, not only do we have specific molarity values for these in our different experiments, but we have rates also. So we can easily solve for K. This isn't any stretch of your mind. Now, look here, focus. Technically, you could use any of the trials to plug in the data and find K. They'll give you the same answer. However, the AP graders, their answer sheet is abbreviated as much as it can be. So they don't have all of the individual intermediate values that you would get if you ran the different trials. Instead, they have all the values for trial 1. They can't take points off if you run numbers on trial 2. But that whole partial credit thing becomes less likely if you're using a bunch of numbers that aren't printed on their sheet. So, here's my advice to you. If you're asked to do a table inspection for a method of initial rates, use experiment 1 when you get to this part of plug and chug. So using experiment 1, here we go. I do have a rate of 1.90 e negative 3. I'm going to set that equal to the variable that I'm solving for. The concentration of NO2 was 0.0482. Times the concentration of F2 was 0.0318. Keep in mind that if these were not both first order, that there would be exponents there. But again, that shouldn't stretch your mind. Like, don't write this, but if you would have found F2 to be to the third order, well, then this number would be cubed. All right, so you'd cube the number and then just do the other math. That's not the case here, but keep in mind that that's how it would be run mathematically. Find an answer, yes?
So if it was a 0, would you just like get rid of it since 1?
It would be 1, yeah. Because, of course, it doesn't affect the rate law if it's a 0 order.
So if we get the answer, is it going to be like this? Is that how we round to a whole number?
No. This will be sig figs, guys. It looks like we have 3 sig figs everywhere. This answer will have 3 sig figs. It's just that intermediate because the orders are always whole numbers. So you should be multiplying and dividing properly. We'll have somebody share a value here in a few seconds. Make sure you have units on your answer, please. All right, let's go over to cluster 3 and talk to seat 4. Oh no, I just shuffled the cards. That's so mean. I hate those cards. Hey, what'd you get?
I got 0.807. I have no idea what the units are.
Anybody get a different number? So, careful with you running your algebra, all right? It should have been this times this would have given you a small number, all right? And then you wanted to divide this by whatever that product was to get K by itself. Would anybody like to share a different answer?
1.2 liters over moles per second.
I got 1.2.
1.24 is the actual answer.
That too.
1.24 is what we were going for there. Hey, have I given you any hints on how to find units of K?
Yes, you gave them to us.
Hey, check it out. It's a second order reaction. Go back to the first slide of this lecture, and you will see that it needs to be
Liters over moles times seconds.
That's like polarity.
Mr. Steve, would I have to use sig figs in these type of problems, right?
you do here, you do.
From where?
From here, look, I have 3 sig figs, 3 sig figs, and 3 sig figs.
How do you know what to divide by? Dumb question.
How do you know what to divide by when running the algebra? Is that what you're asking? So if I change these numbers to simpler numbers, it could have been 8 equals x, 3, and 5. All right? It's the exact same thing, right? So this would have been 8 equals 15x. Do you agree? Do you see how I got that? By simplifying, and then divide by the number connected to the x. In this case, it's a k, not an x, but that's the process. Did that make sense?
Yes, sir.
Why did you take that initial rate?
Why did I take what?
That initial rate?
This one?
Yeah.
Because I could have chosen any of my experiments, but AP wants you to use experiment 1, so I used all of the values in experiment 1. Other questions? Guys, I don't have a way to make this harder. You just need to get good at it. So,
Chilling. I'm feeling pretty confident.
So show me your brain. Look back at the previous example. Look, it tells you exactly what it wants. First, find the order of the reactants. Use that to find the overall order of the reaction. Use that to create a rate law. Remember, guys, this is the rate law. If it ever asks you for a rate law, it's not wanting you to calculate numbers. It's wanting you to write this. That is a rate law. But then if it wants values of things, then you go and you blah, 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 blah. Yes?
I still don't know where to find the first two that you provide.
Okay. So those, if you know how to start, start. If you're confused on where to start, listen. For those of you at home, we're looking at the beginning of the last problem. We have a reaction between nitrogen monoxide and hydrogen. All right. So if right away I'm wanting to start off by finding the order of NO, I'm going to look at the two trials where the reactant that's not NO stays the same. Do you see the two where the H2 is staying constant? 3 and 4. So there's the values. So now I go back to the one I'm looking at. Those are the numbers to divide. Bigger by smaller, and that'll give you your initial number. And then you're going to have to divide again using those same two trials over there, the rates. And then you find that power connection like we did a moment ago. Call me over if you get confused.
You guys always big over small?
Yes, we want numbers above 1.
Hold on. Was that 1.03? Somebody say my name as I was walking with.
Me.
That was fair.
Okay. On the first step, I just want to make sure I don't do that. No, I thought it was
No,
it's the one
because-
that doesn't change.
Right, exactly. But then you go back to the numbers that if you're going to do NO, you're right, you're using this
That,
trials.
yeah.
But you have to use NO's numbers.
Oh, God, okay. Okay.
You really did that.
Right? So you use the two values that you just implemented, and you divide the bigger by the smaller. So yeah. Okay. So initially it was what divided by what? And now we want to find out what to raise that power to make it equal the division of the rates in the exact same. Because you divided the 4 by 3 here, so you have to divide 4 by 3 there. Just between the two trials you're doing, the bigger numbers the numerator. Yes, yeah, but right now you're only doing no. So once you have the order of the reaction, it's like 1 is 2 and 1 is 7. Okay, that's what you're finding right now?
Oh no, I think that's
Yeah, the exponent is the order. Okay. And then you asked me this question. You do this.
Well, yeah, and then that means that okay, so once you just got the second power. It should be two. Can you show me the
Oh.
Yeah, have the order of
No,
each.
just to get to
We need the order of both. Now,
it.
the same thing. Like you said, this is where you're
I could be wrong.
all right, and you're gonna get it right here. It's that number. It's all that.
The overall use of the, I think I'm wrong.
And then what if you do that? No, that's where values Yeah, rate constitutes the K. These are units of K. When you're going to find him, you'll use the two trials for each. What are the two trials that you Not. You should have used three. You used 3 and 4 for him because you needed to. But for him, you're going to use it one of these because you're going to find him.
Yeah.
On your first one, you did it right because you used trials 3 and 4. That's why the other guy didn't.
It's NO2, like, so this is the one, so it's very expensive, which is the one. Oh, okay. Because the order, I just forgot to name my game.
The what?
What's your overall order?
No, because then we only pull coefficients out of negative.
Yeah.
So that doesn't matter.
What's your overall? Overall? I thought the overall order was 3.
Yeah.
So like on the board.
You squared the so it's multiplied by itself. Squared.
Why?
Yeah. No, you're right. You're right. No, bring it together. Because so here, check it out. I'm gonna go 4. I'm gonna go 400
I got my K, my K,
what you want to do. X squared times. Now we'll give you a zero, right? Now you want to divide.
Okay, this is so there's 2 right now.
Because you're doing.
Oh, so it's just yeah.
I'm gonna work this whole problem. Yeah, I'm gonna work the entire problem for y'all. Look how much time we got. I think we're just gonna.
Oh, I missed your comments. I got one question before you.
I'm not starting it.
Okay, I don't have any like bathroom passes yet. I can have the restroom.
Why don't you have any restroom passes?
You haven't given me any.
He wasn't here when you gave him out.
Don't defend Isaac.
Thank you, Lisa.
Yes.
Okay, I'm not sure.
Oh, wait. So you have to first out. I know. I'm sorry. I started eating. I'm gonna get like
I got one. Yeah, so
You got third order?
you put base class. Value on the right hand side.
I got 3 in your
Look at my numbers in the heat.
Oh, wait, remember, you put it.
Oh, it's 7.
You just like is it like you just write the rate low application and the value? What do you want?
So initial rate, I just went.
I don't understand how y'all got 2 for which one? You got 2 for
I got 2 for
It'll be 2. I mean, it's supposed to be 2.
because
It'll be 2.
okay, so you find the ones that are like most alike, right? But on the opposite.
Yeah.
So if you do NO2, then you go to H2, you find which ones are most alike. It is one of these great men, 3 is just And then you go back to NO2, and you divide 300 by 150.
Yeah.
Yeah, that's my whole number.
Yeah, it's two.
Correct order. Yeah, and then you divide the initial rate.
Because that's around
You divide 150.
Oh, the initial rate. That's why. Okay, never mind.
You get 4.
So that's
You all
For NO, you got 3 and 4.
For what?
I did that right. Yeah, you did it.
Oh, you want? I thought we. Okay, I thought we did it for the like. I got NO for 1 and 2, and I did it for the H2 for the NO.
And then for the initial rate, you use the 3 and 4 for NO.
Big divided by 6.
Okay.
Well, technically, one, but just use it. The AP will know how to
But is this the rate law? Huh? Yeah. You just gotta send me. Mr. Cummings, what's the rate law?
The rate law is this right here. This is a rate law.
Did it say rate law question mark? Do we just put that?
Yeah, we want you to write, the correct answer. I'm going to start in just a second.
I know. I'm sorry. I'm just. Yeah, the rate law includes the. Because it actors are both. Yeah. I mean, no, Mr. Conley just did it. So we're a rate like is the 2 an exponent or subscript? It doesn't show up.
It's the exponent.
Yeah, they're exponents.
Yeah. It's not a perfect system. It's just
a system.
All right. Take a look at some data. Working from scratch. In order to start solving some of these questions, starting with order of reactants, I need to take a look at trials where some of the reactants were held steady. So, if we're going to look for NO, trying to find the order of him, I want to find the 2 trials where H2 didn't change. H2 didn't change during trials 3 and 4, so I'm going to use NO data from those 2 trials. It looks like if I do that, I'll have 300 divided by 150, which is going to give me an answer of 2. I want to raise that to a power that equals the rate change for the same 2 trials. In this case, it was 4 divided by 3, so I'm going to go 1.03 divided by 0.25, and I get 4. The question becomes 2 to what power equals 4, and the answer is 2. Therefore, NO has an order of 2. We want the order of the other reactant also. The other reactant is hydrogen. All right. We want to find trials where the NO2 didn't change, and it looks like those will be trials 1 and 2. So I'm going to use H2 data from those 2 trials. So it looks like we'll start with 300 over 150. That looks familiar. But they're from 2 different trials, and I want you to think they're the same numbers. They're not. They're different numbers from different trials. They just happen to reflect the others. I want to divide the rates in the same way from the same two trials that those came from. So I'm going to get 1.34 divided by 0.66. And that equals 2. Of course, I'm trying to raise this number to a value that equals this number of the rate. So in this case, it will be a 1. So I don't show 1s in the rate law. The overall order is the sum of the orders here. So 2 plus 1 is a third order reaction. The rate law, of course, is found by going rate equals K of those expressions reflecting the orders of the individual reactants. But it also wants us to find the value of K. Therefore, I'm going to automatically pick experiment 1 because that's the best practice. So we plug into our rate law. The rate there is 0.66 equals K. The concentration of NO there is 400. All right, and that's going to be squared. Make sure you don't forget that the order is actually a mathematical value, times the hydrogen of 150. Now, I want to point out something that will annoy you. The brackets here are actually wrong because brackets dictate concentration, and this is being given to you in pressure.
I get it.
Again, this problem is being annoying, and most of them on the AP are not annoying. They usually just stick with concentrations. But it's my job to show you everything. But a grader could actually take points away if you use brackets instead of parentheses here. Because if you look at the units given, it's all in pressure, not molarity. And brackets are used for molarity. Doesn't change any of the math. Hooray. Which of course is where the more points live. So, you want to square 400. You want to multiply that by 150. All right? And that will give you value Z, which is going to be multiplied by K. Of course, to get the value of K, you would have to divide by whatever you got there for Z. Z is a made-up variable because I didn't have that number in front of me. But anyhow, it's whatever 400 squared times 150 was. But you will end up with a final K value. I'm going to go to 2 sig figs, even though the work is kind of pushing you towards 1. But I'm going to get 2.8 E negative 8.
Wait, what?
Yeah.
I did everything right.
Wait, let's
Except
use
I
one
did
other
everything else.
Now, if you didn't get that answer for some reason, really from my perspective, it looks like it could be him that messed you up. So maybe you run it again and just be careful with your with your exponent.
Sorry, my calculator.
If you got to the -7, then I mean you might have done 0.6 here instead of 6.6 or 0.06. So I mean, to get really close to the answer but be just a digit off is usually just a count. You pushed the button bad. Yes.
Will there ever be a overall order with a order greater than 3?
No. How are we feeling?
Pretty solid.
Good.
It's better. Yesterday, I feel like you were yelling at me the whole time.
I noticed my grade was down.
Yeah, because he got the
Oh, he knows. Now, before we call it quits, I would like to go over one of the problems that we didn't get to yesterday, but it will take less than a minute for me to show it to you. For those of y'all at home, this is the problem I'm about to project. You can pause and write it down if you need to. Just pass it behind you. All right. Y'all, this is a very simple problem, and there's definitely one on Schoology, so I don't want you to overcomplicate it. One of the reasons this is a great problem to understand is because AP is looking for good math questions to make you answer without a calculator on the multiple choice. And you don't need a calculator for this. All right, you have to run a number, but it's more conceptual than mathematical. So we know that the rate law is the rate and then K and then whatever this guy is, all right, raised to an order. If you read through the wording here, it has you do some very specific things to some of those variables. All right? What happens to the concentration?
It's double.
It doubles. It's times 2. All right? And what happens to the rate?
Times 8.
It goes 8 times as fast. See how you can just translate it immediately into parts of the rate law that you're already familiar with? What's the question want to know?
Order.
It wants to know the order. What is the only possible answer?
3.
3.
Oh.
2 times 2 times 2.
It'll never be anything 4 or above, right?
Right.
Times 2 equals 1 fish and a half.
Computer day tomorrow. Y'all have a great one.